Okay, so moving on now to section 1.6, talking about structs. This will be the last substantial section before getting to the programming assignments and labs and stuff like that. But anyway, so structs in C. Structs in C are almost like, so to speak, impoverished classes. So C is not object-oriented. For that, you need C++. We're going to be working only in C. So we don't have true objects and classes, but structs get you kind of close. They're basically bundles of data. So you can see the abstract syntax of a struct here, but probably it makes more sense if we just jump straight down to an example struct. So you declare struct, the name, curly brace, close it at the end with a semicolon. In between, you declare a bunch of information, not necessarily all of the same type, that you basically want to have bundled all together. So, this struct is supposed to represent a student's data, I guess. So the student should have a name. Presumably, names should not take up more than 64 chars, an int age, a float GPA, and so on. You can declare many instances of the struct, right? So like basically this is defining the struct, and this is then declaring many instances of the struct, namely, student 1 and student 2. You can access the contents of any instance of a struct using a dot syntax that is the same as in a class, especially an instance of a class. But anyway, so this here, student 1, based on everything we saw above, is a struct of type struct student T. If we call the dot age method, then we get an integer. If we call the dot name method, recall that that was an array. So that's the type of that object. And then if we call dot name bracket 3, that's accessing the index 3 of that char array, and therefore what you get is a char. So if we have some instance, student 1 being an instance of char, we call the dot name field. That is a char array. What if we want to fill that with some string? Well, we can use this strcpy to accomplish exactly that. Right, we can use this assignment syntax that is, again, reminiscent of classes and instances of classes. More of the assignment syntax and anything interesting that we ought to talk about. So yeah, maybe let's just remark on this whole picture of how things are stored. This is somewhat like the picture that I drew in the previous video talking about arrays and how arrays basically point to some address in memory where the first element of the array is located. And it has these sort of carve-outs of space sized appropriately to whatever data needs to be there or it expects to fill in those locations. So a struct is very similar, right? A struct, the student 1 struct is going to point to some location in memory. And what this diagram is indicating is that that location in memory will actually be the location of the first field of the struct. In this case, that's the name field. So the first thing that it's going to point to is the name field. And the name field is itself an array, so in a sense, the first thing there is actually the first element of the array. And then it has, spaces in memory that are sized appropriately for char objects, right? The appropriate number of bytes. What I think it was 4 bytes, if I remember correctly, but I could have that wrong. But in any case, we have an appropriate number of bytes so that each of these can store a char, and based on the things that it said earlier about how much memory is allocated, and there will be 64 spaces for a char. So anyway, so what does what is student one? In some sense, it's kind of just a pointer to a location in memory where the appropriate amount of space has been carved out for 64 chars, and then after that, an amount of space appropriate for an integer is carved out, and then after that, an amount of space for what I think it was a float, and then another integer, it looks like, probably. Yeah. So that is what student one, right? That's what a struct is basically a pointer to some space in memory that C has carved out and reserved and will not touch except to be used for this struct, right? So when it, allocates memory or manages memory for other variables, it will not touch the region of the memory that was carved out for this thing. That's basically the idea of a struct. Very similar to the idea of an array, except that an array is always accessed with a consistent type and always in just this like linear sequence of indices, whereas here you have field names rather than index numbers. Let's go ahead and talk about L values. L values are values that can, in principle, occur on the left-hand side of an assignment. So effectively, we have seen some L values. A variable name is an L value because it can occur on the left-hand side of an assignment. And so C structs are L values, right? And ints are L values because, right, a variable holding an int could occur on the left-hand side of an assignment, and so on. So I guess the interesting thing to ask then is what happens when you perform an assignment, right? So suppose that we have done as above, where student one has been populated with all of this data. What then happens if we call this assignment student two equals student one? Effectively, what it does is it copies all of the data in all of the fields of student one and moves it over to student two, right? So basically, it just does a big copy operation. So if this code executes, then student two will look exactly like student one, and then when this line executes, it'll just change the name to Francis Allen, and that's what that does. We'll see again the size of operator. You can call size of on the type of an object, like, right, you could call size of int. I think we've seen that before. You can call size of int, you can call size of float, and so on. It figures out the sizes of these things. It gets more important and more interesting when we talk about the size of a struct, because a struct, depending on the nature of its fields, different structs take up different amounts of memory. And so it's really nice that we have this function that, rather than requiring us to compute it on our own, C offers this function that computes the sizes of things for us. So that's great. And I guess whatever number that kind of thing is inserted into a format string using %lu. I guess here we're going to have a little bit more of a conversation about L values. Single variables of base type, array elements, and structs are all L values. So I think, yeah, right. So, here, the fact that you can do coordinate assignment like this means that array elements, right, because that's an array element. So array elements are also L values. Fields of structs, if they are, integers and such appropriate things, those are L values. The name of a statically declared, it's always worth knowing what is not an instance of a given thing. So the name of a statically declared array is not an L value. So, you don't see us, right, or we could, okay, yeah, here. This is two nicely presented concrete instances of invalid operations because you're doing things, right, you're doing assignments to things that are not L values. So this is not an L value because, x plus 1 just is not an appropriate thing to do an assignment into. right? It's a valid expression in other settings, but not on the left-hand side of an assignment. X by itself isn't a valid thing, but anyway. So that's not an L value, and therefore this line of code is invalid, would cause an error. An array, even a char array or anything like that, doing an assignment is not valid, right? And this has to do with the fact that, the arrays are, basically addresses in memory or, something like that. So anyway, you can't do this, right? If you want to fill an array with some data, you have to either use stir copy, or you have to one coordinate at a time, assign the values into it or something like that. So let's look at this one. Why is this one not right? Why is this invalid? The name field is not an L value. Why? The base address of a statically declared array. That's what student1.name is, a statically declared array, because it is a char array. So that's a statically declared array. That's why this is invalid, because this is not an L value, because it's basically an array. Passing structs to functions. Again, we're coming up against this issue of pass by value versus pass by reference. I think the long story short here, since we've already really discussed this quite a lot, so I think I can simply tell you that when passing structs into functions, this actually does go in a pass by value kind of way, which is to say that rather than copying the address to the data, it actually copies all of the data. It gets a new instance of the struct. So let's just read this though. So because the value of a struct variable represents the full contents of its memory, passing a struct into an argument gives the parameter a copy of all the argument struct field values. If the function changes the field values of a struct parameter, the changes to the parameter's field values have no effect on the corresponding fields of the argument. That is, changes to parameters fields only modifies value in the parameters memory locations of those fields. So yeah, I think this is basically agreeing with my description. So let's look at this instance, right? So we're gonna define a struct. Later on, we'll define what this function is. And in fact, I actually want to see it before I look at where it gets called, because let's come down here and look at the definition of this function. So what does it do? You pass in a student struct. You pass in a min age, okay? You declare this integer variable equal to 1. If age is less than min age, then you set the ret value to 0, and then increment the student's age. And in particular, right, this is the interesting line, I would say, because this is where we are actually mutating the values of the field of S. So the question is, if this function executes this line and changes the age field of S, are you going to see that change when you have actually exited the context of the function call and go back to the sort of surrounding context? So with all of that having been observed, let's go back to the main function and look at what it does. Okay, so what do? We declare an int variable, declare a student struct. We copy over its name, sure. We give it an age of 17. That's going to be worth noting because down here we're going to pass in student, and we're going to say that its minimum age, the minimum age of a student is 18. And what that means is that s.age is 17, min age is 18. This is going to evaluate to true. Therefore, this body of the if condition is going to execute. And in particular, it's going to take age and increment it by 1. And then it's going to print the result, right? This print call comes from inside the context of the function, but that's all going to happen. And then we exit, right? Eventually this function call exits and we move on to the next line. So we're going to check if can vote. So where did can vote get determined? It was a variable up here. Did it? Oh, right. It is assigned a value by this function, which is going to return true or false. And so here, it's going to set ret to 0 and return ret. So it looks like ret is going to be 0, and we're going to go into the else clause. And so this is then going to print that the student is only this many years old. Thinking about everything that happened, like let's now that we've done one walkthrough, let's kind of summarize. It goes through all of this stuff in this line because it kicks over to this function, and all of this executes. It should print that the student is this many years old, where this many years old is s.age. S.age became min age plus 1. Min age was 18, so min age plus 1, that's 19. This value should be 19, okay? That's the first call to print. But then we exit the context of the function, right? At this point, we now exit the context of the function. We check the if condition, it fails, and therefore we go into the else condition. And now this line of code is going to execute. Now, what is this going to do? It's going to say the student name, yet again, that never changed, so that's going to be the same as always. And then it's going to use student.age, and kind of the question is, what is that value going to be? Is it going to be the 17 that it was before the function executed, or is it going to be the 19 that was assigned here inside the function? And the answer is that because structs are passed by value, you're not going to see that change, and this is going to be 17, just like it was before calling the function, right? The function call does not change that field once it leaves the context of the function. And so this is confirming everything that I said, right? The first function call is going to print 19. The second function call is going to print 17. And this is, again, an execution stack diagram. Initially, main is called. It creates the student, ret. So this diagram is showing the state of the computer before ret has been assigned, right before the call to check ID has completed. But because this is up here, we are seeing the state of the computer basically like right at the end of check ID finishing its function call. And so what's going on up here, there is a copy, right? Not pointing to the same place, right? Remember in an earlier diagram, if this variable were pointing to the same address in memory as it would with like an array, then you wouldn't see a copy up here. Rather, the diagram would just show you an arrow going from S down to here, right? That's what it did with the diagram for an array. But that's not what's going on here, because with structs, C is passed by value, and so it makes a copy. And that's why you see a copy up here. In the copy, the value of the age got updated or assigned to the value 19. And I guess what else is there to say about that? Not much, except just to notice that that change never trickles back over to student, because again, it's only editing a copy. It's not editing this location in memory. So again, just really beating this dead horse of the whole topic of pass by value and pass by reference. Okay. And I guess that's basically the end. So in the next video, we should finally get around to doing stuff.